To our dense granular flows workshop. So before I say a few words, we're going to have a welcome from David Wallace. So David Wallace, the director of the Isaac Newton Institute.
Thank you very much, Ricky. Just a few words of welcome from me before you start what looks like a really interesting conference. I'm rather relieved, actually, to say I think it just about is a warm welcome. So after the Christmas and New Year break, actually, the heating appears to be working well, so that side of it is okay and no frozen pipes or whatever. Just to explain, because there will be some of you who haven't been at the Newton Institute before, we are a standalone, separate institute, separate from the two departments. But I'm employed within the University of Cambridge, and we typically provide programs of 1 to 6 months long, 2 programs at any one time for up to 40 visitors, plus workshops within the programs. So normally we have long programs of 1 to 6 months, because shorter programs are typically supported at the ICMS in Edinburgh. So what are we doing with this 1-week program here? Well, we had a bit of an interaction with Ricky and Jim and colleagues, and actually realized that the best way to look at this is actually as a follow-up program to the granular flows, long granular flows program, which was held here in 2003. And so my first message, I guess, is just to say that I'm really delighted that we are supporting this workshop with the £5,000, and I hope that has actually helped some of you to participate. That's what it was meant to go, Ricky, actually, just to be very clear. So I hope that really has gone. So I really hope that it really has helped towards the expenses and the subsistence costs here in Cambridge for some of you. And I would say that follow-up programs are a great way for us to get some pull-through from earlier programs. I know there are organisers here from that program. It's a great way for us to get pull-through for people to renew collaborations, etc. So we have a policy of encouraging follow-up programs like this, and they don't necessarily have to be at the Newton Institute. We are willing to support follow-up programs elsewhere as kind of satellites. So that's something that you might want to bear in mind, some of you, more widely. I know this is an Institute of Maths and its Applications workshop. You've got organisers here or administrative staff here from the IMA, and that's great. I'm sure they will do everything that they can to give you an effective and enjoyable time here, as will all the staff at the Newton Institute. Our whole role at the Newton Institute is to make visits worthwhile and interesting. So if you have any questions, please just don't hesitate to ask. I have a final sort of thing that I really ought to say, which is the health and safety staff, that there are obviously 3 exit doors in this lecture theatre. If you're operating more generally within the Institute, do be very careful about trailing cables on laptops. I just have this nightmare about somebody tripping over and heading over one of the banisters downstairs. No, I don't want to think of that. So be very careful with trailing cables. And if there is any fire, please be aware that you do not have to use the main staircase. There are actually fire stairwells in these 2 corners of the building. So please be aware of that. But I think that's probably enough from me. I'm very grateful to the organisers and the fact that you're all here and getting us off to such a great start. So I'll leave you to it and hope that you have a really interesting week. And thank you very much, Ricky. Thank you.
Okay, so I'll just say a few words. Thanks again to the INI for giving us some funds to support people, but I should also mention that the IMA is also, of course, supporting the conference. We have funds from NSF and also the EPSRC, so we're very grateful to the support that all those organisations have given us. I have a few things to mention. Of course, we're going to have coffee breaks and lunch breaks and so on. Everything is contained within the Institute, so there'll be coffee, I think, just next door, lunch in the room over here, and then, of course, the evening meal for those of us that are accommodated within the hall will be within the hall itself, where we had breakfast, if you were there. For the talks, I should mention that they are being filmed and they are being recorded. So if I could ask all the speakers at some point to just sign one of the forms that are collected over here, just to give your permission for the audio recording. And so that needs to be done before we can take the recording. And of course, for the recording, there's a microphone, so everyone will need to be mic'd up just before the talk. As people have mentioned to me, we have a very full program, as you can see. So I'd like to request that we're very prompt with finishing and starting, and there'll be a very sort of strict few minutes of question and answer that I hope the session chairs will be moderating quite nicely. So, finally, if you have any questions, please don't hesitate to ask me or Jim McElwain or Nico Gray and John Huntley when he's around. And for administrative queries, please do ask Sammy or Amy from the INA outside. So all that's left to say is I hope you have an enjoyable experience in the week, and you get to meet people that you've not seen for a while or you've never met before, and have some good interactions. So without further ado, Raffaella, our first speaker, please. Sorry.
Okay, good morning to everybody. Can you hear me? No.
It's not a microphone, it's just a recording.
Right. Oh, good. Okay, so it's really a pleasure to be here, to see some of my friends in this room. I was one of the lucky ones who took part to the program in 2003. And I think that when we had this meeting here, it's nice to be back, I think. And some of the ideas that actually have been developed here came just from discussions with my colleagues here at the Isaac Newton Institute. The other thing that I would like to tell you is that I just came back from Italy last night. I haven't spoken any English for the last 2 weeks. And I have an excuse today just for a change for my very poor English. So I hope that you can bear with it. Anyway, since I'm coming back from Italy, I thought this is the first lecture in the morning, and I thought that probably it's nice just to wake up in a different way. And my talk, it's about modeling. And being about modeling, we do think that modeling is something that we do just nowadays, but actually I think that also long time ago, and of course, I mean, being Italian, I'm very, very fond of Leonardo. People were doing modeling, and that's the model of a bridge that Leonardo tried to convince the Sultan to build on the Golden Horn in Istanbul. However, there is an analogy here. People never believe in models. The Sultan never believed in that model. The build was never actually built. However, only recently, somebody, an architect in Norway, saw the model of Leonardo and tried to build it. And actually, this is what the bridge looks like today. It works, perfectly works, without any experimental validation. So I think that there is a good hope that the models that we do probably can work. And Leonardo, I think, realized that small models sometimes can work, and they are really the ones that we should look at before we actually model the big system. This is just like I said, a little bit of introduction to say that, what I want to do, I want to describe a very complex system, and what I'm trying to do, I'm trying to represent it through a model. And then there are different viewpoints, and today I'm going to show you just one of the viewpoints, the way I do some kind of modeling. And of course, I mean, it's not unique, it's not the only way to solve the problem, but it's a way to do some investigations. Now, to give you a little bit of background and go now finally into the topic of the talk, granular materials. Well, granular materials, we all know that might behave in a in a very different ways, in a very different way. And it depends really what kind of flow they undergo. So they can undergo slow flow, and the particles in this kind of regime, they are really undergoing non-impulsive and finite contact interactions. This is the regime where usually we do use what is called frictional laws, and we take these laws usually from Coulomb. Fast flow is the other extreme, where the particles really move very fast. They are very agitated. They can collide with each other. They can move around freely. And usually we assume that the contact between particles is of infinitesimal duration. Of course, I mean, when we try to model the two regimes, what we do, we use constitutive equations. And the constitutive equations have to take into account what really is the kind of interactions between particles. And as I said, in the slow regime, we have frictional stresses. Usually, in the fast flow regime, we have usually kinetic and collisional stresses. The challenge here is really to develop the methodology and what of approach, and as I said, there is not a unique way of doing that, but we use the volume average, continuity, and momentum equations, what is also called like the two fluid models. We have to identify what are the relevant mechanisms which are responsible for the behavior, and of course, I mean, we have to model the mechanisms. And we have to model collisions, frictions, gas-particle interactions, and sometimes cohesion, and so on. We have spent quite a lot of time, actually, to identify what are the real mechanisms which we should consider. And I think that there is still a long way to go, because there are still many investigations that need to be done probably at the particle level, which can give us a much better understanding of what really is happening among particles. Telling you just a little bit the way we do solve the problem, we do assume that what is called continuum modeling. These are the particles. I don't think I need to go very much in details through this, because this is really, I mean, this is my audience is of experts today and that is really very nice. But anyway, just briefly to review a little bit the way we do the modeling. These are the particles which are in a duct, for instance, in a tube or whatever. And the particles are considered to be like a collection. All the collection of particles are considered to be as a continuum. And this is why we can actually write momentum balance for what we call the particulate phase. And the two phases, the gas and the solid phase, are considered as a two interpenetrating continua. Of course, I mean, I think that all over, this is the important step. And this is where we have been concentrated a lot in the last years, writing down the constitutive equations. The other thing which I forgot to say is that in order for this kind of modeling to be sort of valid, and here there are many questions, because of course, I mean, there are people who don't believe in this kind of modeling, and however, I think that the most important thing is that we have to make sure that we are dealing with a system such that all the length scales are taken in the right consideration. In other words, we do make averages on a volume, a control volume, which does contain enough particles. Because of course, I mean, if we go on a scale of the particle length, we lose the possibility to make this kind of averages. And of course, I mean, one of the major problems is just to write the boundary conditions, because of it does saying at the wall, it doesn't mean anything. You really need to consider a zone which is very close to the wall, but still contain a significant number of particles. I'm not going to go in much details through the equations, at least at this level here, because as you will see, I would like just to concentrate to one of the issues that we encounter during this kind of work. And the issue really, what I've done so far, I've presented you the two limit, the slow and the very fast flow. And what I'm going to do now, I'm going to present you the equations and show you how actually, again, these are limits, but there are situations in between that we weren't up to some time ago we weren't able to model, and we hope that we have tried to model it in a more realistic way, but probably this is not over yet. Anyway, this is as I said, we have to write governing equations, and this is the continuity equation, and it's written for the gas and the solid. And of course, I mean, the index is here, just indicate the two phases. Epsilon is the solid volume fraction, density, velocity, and here the gas and momentum equation, the gas solid momentum equations. Again, these are for the gas and this is for the solid. And as you can see, well, all very well known terms. You can see the stress here for the gas, which doesn't give usually any problem, and you can see the stress here for the solid. And actually, the big problems arises when you try to write equations, constitutive equations, to close the balance equations for for the stress here. Again, this is the drag force. Everything probably can be written in a sort of straightforward way. However, when we do go and try to express these two terms in terms of the characteristic of the system and what the behavior of the system is, the real problems start to arise. I put just here, I don't spend much time about, again, the details of the equations. I didn't write down the energy equation, which has to be supplied to these equations here, to the momentum and the continuity equations, only because they are, when we try to express these two terms here, and some other bulk properties of the gas, of the solid, we do need to introduce what we call granular temperature. I'm careful now, I don't call it anymore pseudo temperature because people don't like it so much. But anyway, granular temperature, which is nothing else than a measure of how the fluctuation velocity of particles. Now, as we said, there are situations where particles can be very close to each other, the flow can be very, very dense, and therefore we need to take into account the fact that there are some frictional stresses, which are the dominant ones. There are situations where the particles are, the flow is very dilute, so probably the kinetic and collisional models can be okay. However, of course, I mean, you do realize, and this is the first problem that we started to have really long time ago, and actually these kinetic collisional plus frictional models, which is called also additive model, dates back to very long time ago. My PhD thesis last century was on this one. Yes, it was. It was on this kind of approach, and that's exactly what I did. I mean, I just put the two contributions together. The two contributions together in a very simple way, actually. And what we were saying at that time, well, if there will be a critical value of the solid volume fraction, if that critical value is exceeded, therefore you do really switch to the other regime. So it was not really any kind of modeling of the intermediate flow. You say just this is the flag. From under this value, you have kinetic collisional flow. When you reach these values, then you switch to the frictional flow. And here, of course, I mean, you can write, this theory was developed in 1984, I think, and this is really the soil mechanic theories, and these are the classic equations which, well, there are many derivations, but usually we did refer to Lan and co-works in 1984, I think. Now, if now here we started to do some calculations, and what we observe here, if we take the kinetic contributions and the collisional contribution and the total one, this is what we have for the shear stress versus the solid volume fraction. The only reason why we did this, we want to see how much the kinetic and collisional stresses contribute to the total stress. Now, as I said, collisional, as the word says, just the stress which arises from the collisions between particles, couple of particles, two binary collisions. The kinetic stress is the one which is just because particles are moving around, bringing their own kinetic energy around. So it doesn't involve really directly the collision. Here we have plot just the shear stress versus the solid volume fraction. When we put together, this is the kinetic frictional additive approach. This is just the frictional, and this is the kinetic. So as you can see, the additive approach just takes switch at about, well, it depends. Some authors takes 1.5, some 0.55, 59, and so on. So it's really in this area here that we have a sort of flag where we just say to the program, well, go to the other way of calculating the stresses. Intermediate regimes. Now, we looked at that data. We did number of calculations. This is not just the thing that we calculated. Of course, we calculate the velocities, we did the flow maps and everything. However, I think that there was a clear indication that something was going on between the two flows. And actually, it's the reason why we started to realize that was not really very much for the kind of flow that I will speak about today, which is really the horizontal flow. But it was, and my co-author is just in the audience. I mean, this work is really very much the work that Yassir over there did when he was at Heriot-Watt. We started to investigate for public beds. And we had some strange situations around the bubbles. And we started to try to understand what was going on. And there was this region where, the flow is not very dilute, the particles are not very dilute and not so dense. And then this is why we start to think, well, probably there is an intermediate regime there. And at the same time, Gabriel Tardos in USA also started to investigate this kind of regime. And I remember that we had, now I can't remember which year, but I remember we went to an IFPRI meeting in Germany, and we were discussing, Ricky was there and Roger was there, and we were discussing this intermediate regime. So we are aware that actually the slow and dense regimes are very ideal situations, which we have idealized in our mind. But of course, I mean, something exists in the between. And the additive approach is not really, it's a way of cheating, I suppose, because really it's not really modeling what is in between the two regimes. Now, this one is redone, this kind of diagram just summarize a little bit what I was trying to say here. And as you can see, there is quite a big zone here where we really should consider the intermediate flow, and we don't know very well how to model it. Now, in order to address the intermediate flow, we started to think of doing our calculations on a one-dimensional, fully developed flow model in the horizontal duct. The reason why we decide to have the horizontal one, as you can imagine, it's a very nice way of investigating the intermediate regime, because close to this wall here, you have very dense flow. At the top, you have very dilute flow, and there are all situations in between that you can actually think, well, this is probably intermediate flow. So this, again, we wrote the usual equations for the two phases. This is the gas, and we, well, nothing much about this, except that we use the expression for the gas, which is modified for the presence of particles there. And this is the y component of the solid momentum for the gas, with the two contributions now here, kinetic collisions and the frictional, and this is the gravity. Again, it seems like written in this way. Still, I mean, we have the kinetic and the collisional ones in this additive way. Solid x momentum. Now, here it comes. It's a very busy slide. Let's try to see what I'm trying to say here. This is the kinetic component of the solid momentum. This is the frictional component. Now, here there are different kinds of approaches. There is the critical approach, which originally was done by Johnson and Jackson, and as I said, I use exactly the same methodology in this kind of problems, and this is really the Coulomb law. Tardos in 2003 developed a new way of approaching this frictional component, and as you can see here, there is really a new way of relating the frictional to the pseudo temperature. And the good thing about this kind of methodology is that now you have A, which can change by changing when the pseudo temperature or granular temperature changes, and therefore this equation here only in the limit when this is equal to infinity goes to the Coulomb law, which is you recover the right limit. So just keep in mind that expression for the time being. And then the kinetic, the energy balance, as I said, we need to write, because we have that T that we need to express. We have the additional unknown T, so this is why we need an additional equation. There are, again, two ways of writing the energy dissipations now. This is the original one, which comes from the kinetic collisional model. This is the one which comes when you use the Tardos approach. And again, you can see that there is a contribution which is more or less important depending on the values of A. Now, this energy dissipation, I should say, it's a way of saying that particles-particle interactions are not perfectly elastic. In other words, there is a loss of energy when particles collide with each other. And this is why, of course, I mean, here in LAN approach, there is just the kinetic, the collisional theory which is invoked. And here, there is something else because it considers also the fact that, you know, there might be situations where you are in between. Again, want to just show you this is the Tardos expression, and this is actually written for one-dimensional flow for the kind of geometry that we are considering. And again, now we have theta here instead of t because we make dimensionless the system. But anyway, this is what I want to say here, is that by varying the standard deviation of the strain rate, you can actually vary the contribution to the stress here. Calculations that we have done. Red is the equation that I have just shown to you. This is the classic kinetic theory. This is Johnson and Jackson. Johnson and Jackson. And this is Janicki. Just we were considering different kind of theories and trying to see what the contributions of the different theories was. And then just to see how the particle shear stress compare to each other. And as you can see, we identified zones here where actually the two expressions, the one for the kinetic and the one kinetic collisional expression and the one from Tardos are not really giving the same kind of values. Next thing that we did define the transition regime, and just because we want to give some sort of guidelines of when we are starting to go from one regime to the other one. As you can see and read here, what we said, we actually say that we are in the intermediate dense regime when calculating the two stresses, like from the kinetic and theory, and the one from Tardos, the stress exceeds, the one calculated by Tardos exceeds the kinetic model. And it does exceed because, of course, there is the additional contribution due to the frictional stress there. And of course, we do say that we are in the quasi-static regime where we don't observe any dependence from the shear rate anymore. So in a certain way, we have the extreme here where we are really in the intermediate, in the slow regime, and we are switching to the other one. Now, this is what I was meant. Here is the switching point. This is the classic kinetics. This is Tardos. This is the expression of Tardos when you write it for a very general geometry. What we did with Yassi over there, we did assume that in our model now that when we calculate the switching point, we take the maximum between what you actually have, between the kinetics one or the Tardos one. And again, this is just the simplified version that I presented before for Tardos approach. Here, just a comparison again with the other theories, and again, this is where we switch to the intermediate flow. This is what we consider being the limit for the intermediate flow. We did calculate the flow operational map for horizontal flow, and as you can see, they are quite different results which come out from the different theories. This is the frictional additive approach. The classical kinetics model, as you can see up to here, and here you have really to zoom. There isn't really any difference if you consider the additive of the collisional only, and that's because the limit where actually things are happening is so small, the region where things are happening just here. This is the smooth transition through Tardos, and this is what we actually have with another approach, which is very similar again to the additive approach. So it's just the comparison between the different approaches. So of course, I mean, this is the flow rate of gas versus the flow rate of solid, and for each one of these points, you can calculate what the flow is, and you can show profiles of velocities for the two phases and whatever you really want. Just to give you an example, this is for instance the granular temperature along the duct, and you can see that if you have just the additive approach, you have this kind of behavior. If you now consider the new approach that we have modified into the model with Tardos equation, you have this other behavior here. Here again, this is the solid velocity, and this is the solid fraction, and I think this is probably the very interesting one, because here you can see that there is no such unrealistic actually behavior close to the upper wall, despite the boundary condition stays the same. So this is what we obtain for the new model. We actually also did a little bit of calculations on the stress, and this is the friction to kinetic stress ratio. This is what you obtain if you consider the original way of doing or adding the contributions. Here is what you obtain actually now with the modified model, and you can see here it's a very difficult zone which we should enlarge, but as you can see, as you expect, it goes from very dense to gradually to the dilute one, and therefore it's much better way of representing the reality. Here it's I mean, this area here was a little bit tricky for our calculations before. We did try to, well, we presented a couple of papers, and one of the papers was accepted with no any change, which we were quite amazed. Another one came back saying, you have to do some experiments. So we didn't have any experiments. We went back. We tried to look at what was available. We tried some kind of experiments. We find some papers here, and we tried qualitatively to draw what we had from the papers there, and we tried to reproduce the same kind of behavior, the same kind of diagram, sorry, for our situations. And as you can see here, again, this is the modified model, this one, the red one, and this one is the classic kinetic theory, and we tried also to plot the velocities, the stresses, I think it's this one, and the solid, I can't read myself. No, I think this is again the stresses, yes. But what I'm trying to say here is that our model was much more close to the values that we found in these papers here. The predicted shear stress in horizontal flow, again here it's another way of looking at the different models together. And of course, I mean, we did that just to see how, when we were switching to the other regime, and the intermediate range was quite large. So it's not just a very small region, but it's a very large one. And it's indeed, we think that it's between this 0.1 and 0.5. We also did plot the shear to particle pressure here. We had some strange results in this limit here, which actually would be nice to discuss with you, because we thought that this is the explanation. We observe with this modified model this sort of behavior here, very large concentrations. This is the kind of explanations that we tried, saying that when we are at very large concentrations, these are front and back collisions between particles within the same layers and the top layers, and then it gives rise to an increase on the particle pressure, and therefore there is this sharp decrease in the pressure ratio when we are at close packing conditions. So this area here was a little bit tricky. And finally, we tried to put together everything we had, because we thought that probably when you want to apply really your theory, you have to give also some sort of guidelines. And what we did, we tried to plot what we had obtained for the different regimes, and try to extract in terms of a modified Reynolds number. There is the relative velocity instead of the gas velocity in the Reynolds number, and in terms of the dimensionless shear rate, what are the limits where we should start to consider the intermediate regime. And what we found is that the dimensionless shear rate should be in this limit, and the Reynolds number, the modified Reynolds number, should be in that limit. So it's a way of concluding, saying that these are actually the conclusions from our calculations, which we do believe are a good guideline, at least for what we have observed so far. So conclusions here, I don't really need to read them. It's exactly what I have said a few minutes ago. And two things very quickly. First one, but very important, acknowledgement to Yassir, who is over there, and as I said, he did most of the calculations. And finally, oh God. And finally, I would like to leave you with this, going back again to complex systems, where we do know that there are many descriptions, and we don't know which one is the real one, except when we do experiments, which we haven't done. Thank you very much for your attention, and I'm on time.
Thank you. Do you have any questions for Raffaella?
Okay, I'm trying to remember back to Gabby's paper, but there's a problem here with the use of granular temperature if you want to go across the regime boundaries. In the kinetic theories, the granular temperature represents the relative velocity between individual particles. When you start going across the regime boundary, it can't be that. And if I remember Gabby's paper correctly, he actually started with this paper of Stuart Savage's, and where Stuart was talking not about granular temperature, he was talking about strain rate fluctuation. And in Gabby's paper, he more or less said, I don't know what to do with that, so I'm going to use granular temperature instead. And can you comment on this? Are we getting ourselves into trouble here?
Well, I think you are right in describing what the development of Gabby's paper was. And I think, well, I haven't read it recently, the paper myself, but I can remember now that you mention it, I can remember it. So, well, I think it's a very fair point, what you are saying, and I do think that I do personally have a difficulty with this temperature myself, with the granular temperature, because of course, I mean, strictly speaking, you're right, you can consider it only when you have the conditional theory, which that is originally when it was expressed. I think in any event, that's a parameter there which do represent some sort of behavior of the system, which has to, well, which we try to model with the granular temperature. I don't know. I mean, it's like I said. I think it's a fair point. But if we don't try to do something about the problem first and try to see what the model can say, I mean, I don't have any other way to do it. Probably we have to investigate better the particle level. At the particle level, what's happening? I do remember that Gabi referred to Savage, and in fact, I think one of the coefficients is taken from him. I think that Gabi also has the strength of having some very nice experimental results in aquatic flow, and it looks like his development works. So the paper, if you remember, it's not just the development, there is also quite a strong experimental support of what he's saying. So,
can I make a remark just on this? I think it has to do with a different way of closure. Like in turbulence theory, the granular temperature is a measure of the kinetic energy of the temperature fluctuations. Well, if you take the gradient of the temperature fluctuation and make the dyadic product with itself, you get a tensor, a symmetric tensor, and that is, it corresponds to second order closure in turbulence. And I think Gary does that, or something similar to that, and Savage used the granular temperature, which is a low order closure condition. And so you cannot compare the both of them, because they are different measures of turbulence, of
well, it's
of
different
impact.
measure of that kind of,
Yeah.
But as I said, I think that it depends really what you want to model. And from my point of view, while I do appreciate the work by Savage, I do think that Gabi, with his experiments, shows that, you know, at least for that particular situation, it was, I mean, the theory is okay. I mean, the paper is very much experimental as well.
Well, this is an indication that you may need in the theory a closure, an additional closure variable,
we can
which is symmetric tensor.
Absolutely, because, you know, we did also had some similar issue, which is, well, it's only similar, it's an analogy, when we started to do cohesive interactions. And then if you do start to consider the temperature, you have to go to a higher order of granular temperature. You have to start to consider the difference of the temperature between layers, and then at that point you go to the gradient and blah blah blah. So it depends on which order you want to stop. I believe. I consider. I think, but I don't think that's the end of the story anyway, because it might be that that's not. The second order is not even what we want. I don't know.
But that's all in a fast regime.
Yes.
If you go to the quasi-static regime of the slow regime,
it's not the second order.
The concept of granular temperature or any correlation tensor you construct out of these fluctuations loses
Absolutely.
its meaning.
In fact, we had just zero there. Yeah.
Anybody else? No? Okay.
I have
Everybody looks for.
I don't want to dominate this. I'm talking about the similar thing in the thermodynamic basis of what you have done. Those merging of the quasi-static and the dynamic contributions. Are these essentially fetch factors you add to the stresses, to the quasi-static and the dynamic stresses, that make the transition from one regime to the other smooth?
Well,
Well, you said in your dissertation it's essentially, how can I say, it's if it's not a smooth transition, it's abrupt. If a certain variable is below a certain value, you have the quasi-static. If it's above, you have the dynamic situation.
It's a smooth transition.
And the transition has to be smooth, so the quasi-static stress, its contribution has to go down as the process becomes more dynamic.
It is, well, the switching there is just a way of saying when we are, to give the guidelines when we are going to the other regime, but it is a smooth one, because you have that sigma that smoothly varies, so it's not an abrupt
Only
regime.
experiments are the judge to decide which one of the proposals of these
Oh, absolutely.
smooth transitions is correct.
Absolutely, I agree with you. In fact, I mean, this is why I think that we try to look at some of the experiments that we could find, but we don't have any other experiments. So which one is the right one? I agree. It's only the experiment that can say. We don't have any validation at the moment. We have partially validation, so it's a matter of having more experiments to say.
Have you attempted to make any contact with the modeling in terms of the inertial parameter that has been carried on recently? There's lots of numerical simulations and some experiments there.
No.
It seems to me they're addressing some of the same regimes that you're interested in.
Okay, thank you.